Hello everyone. We continue. Welcome back to this chapter on eigenvalues and eigenvectors. This is lecture 12, capsule 12a, and the theme is diagonalizability of matrices. Diagonalizability of matrices is a very important theme in linear algebra. It has got numerous applications, and there are lots of applications to differential equations, for instance. And let's get to the bottom of the thing right away. Before we introduce diagonalizability, we would need a certain concept known as similarity. So when are two n cross n matrices A and B similar? Two matrices of the same size are said to be similar if there's a non-singular matrix P such that P inverse AP is B. Of course, P must also be n cross n, otherwise the product doesn't make sense. So this is a notion of similarity of matrices. Observe that if A is similar to B, then B is similar to A. Why? How do I get the reverse one? A equal to PB P inverse, and P can be written as Q inverse. So write P inverse as Q, then PB P inverse is Q inverse BQ. So there exists a non-singular matrix Q such that A equal to Q inverse BQ. So if A is similar to B, then B is similar to A. A is similar to A. Why is A similar to A? Take P to be the identity matrix. P to be the identity matrix. If A is similar to B and if B is similar to C, prove that A and C are similar. So the similarity relation is a transitive relation. Let us look at one of the basic properties of similarities. Suppose if V is an eigenvector, of A with eigenvalue lambda, what does it mean to say that lambda is an eigenvalue and V is an eigenvector corresponding to it? It means AV equal to lambda V. Now I'm going to introduce a PP inverse in between. So I'm going to write it as A times PP inverse of V equal to lambda V. A times PP inverse V equal to lambda V. And then I'm going to pre-multiply by P inverse. So I'm getting P inverse AP applied to P inverse of V equal to lambda applied to P inverse of V. But what is P inverse of A? What is P inverse AP again? P inverse AP is B, remember? So B applied to P inverse of V equals lambda applied to P inverse of V. So we have proved that P inverse of V is an eigenvector of B with the same eigenvalue lambda. Of course, before I conclude that P inverse of V is an eigenvector, I had to answer a question. Remember, how do I know that P inverse of V is non-zero? Well, if P inverse of V were 0, then P applied to P inverse of V will also be 0, in which case V itself will be 0, but that is false because V is an eigenvector of A. An eigenvector is not supposed to be 0. So we have answered we have answered that question, and we are concluding that P inverse of V is an eigenvector of B with eigenvalue lambda. This is a very simple observation, and this simple observation will be needed in the problem of diagonalizability. Now, similar matrices. For example, if I take the determinant of B, what is determinant of B? Determinant of B is determinant of P inverse into determinant of A into determinant of P. And determinant of P inverse and determinant of P will cancel out, and determinant of A will be equal to determinant of B. Similar matrices have the same determinant. Similar matrices have the same trace. Prove that similar matrices have the same trace. So now let's come to the main theorem. For n cross n matrix A, the following are equivalent. There is a matrix P such that P inverse AP is a diagonal matrix. In other words, A is similar to a diagonal matrix. A is similar to a diagonal matrix. And the other condition is there is a basis consisting of eigenvectors of A. There's a basis consisting of eigenvectors of A. Now we have to show that these two are equivalent. So before proceeding to the proof, let us observe that there are matrices for which there are matrices for which the second condition fails. There's a basis of Rn. There's a basis of Rn consisting of eigenvectors of A. This condition will fail for certain matrices. And here is an example of a matrix A equal to 0, 1, 1, 0. What is the rank of A? 1. What is the nullity of A? 1. So there's a non-zero vector in the null space, and that non-zero and that vector is 1, 0, 1, 0. E1 cap is even cap is in the null space, and A even cap equal to 0 even cap. So 0 is an eigenvalue. There are no other eigenvalues. You can calculate the characteristic polynomial. You can check that the characteristic polynomial is x squared. 0 is an eigenvalue, and there are no other eigenvalues. So if you want to find an eigenvector v, then that eigenvector v has to satisfy AV equal to 0v. That means that eigenvector v must be in the null space of A. That means that eigenvector v must be a multiple of E1 cap. So the nullity is 1, remember? Nullity is 1. So the matrix has only one eigenvector up to multiples. That is, you cannot have you don't have two linearly independent eigenvectors, and therefore you don't have a basis of eigenvectors. R2 is a two-dimensional vector space. R2 is a two-dimensional vector space. R2 is a two-dimensional vector space, and so it must have, if you want a basis consisting of eigenvectors, you must have two linearly independent eigenvectors. But there's only one eigenvalue, 0, and so the eigenvectors are all in the null space, but the nullity is 1. So it's not possible. It's not possible. This matrix has only one up to multiples, up to scalar multiples. It is only one eigenvector. So this does not satisfy this condition that there is a basis consisting of eigenvectors of A. In other words, this matrix is not is not a diagonalizable matrix. A matrix which satisfies these conditions, these two equivalent conditions, is called a diagonalizable matrix. So this matrix is not a diagonalizable matrix. Okay. This matrix has a peculiar property that you cannot find two linearly independent eigenvectors. So such matrices are quite tedious to handle. Matrices for which there is a basis consisting of eigenvectors of Rn are pleasant. Matrices consisting for which are diagonalizable are pleasant objects. Let us get to the proof of the theorem. 1 implies 2. 1 is what? 1 is that A is similar to a diagonal matrix. That means there is a non-singular matrix P such that P inverse AP is lambda 1, lambda 2, lambda n down the diagonal and 0 elsewhere. That means what? AP equal to P times the diagonal matrix. Okay. Now, you have got these two matrices are equal. So let us apply these two matrices to even cap. So AP even cap equal to P, the diagonal matrix, apply to even cap. When I apply matrix to even cap, you simply get the first column of the matrix, basic rule number 1. So AP even cap equal to P applied to lambda 1 even cap. The first column is lambda 1 even cap. But what is P even cap? P even cap is the first column of P. And let us call the first column of P as C1. So AC1, LHS is AC1. The right hand side, the lambda comes out. It's lambda times P even cap, which is again C1. So AC1 equal to lambda 1 C1. So the first column of P is an eigenvector of A with eigenvalue lambda 1. Similarly, the second column of P will be an eigenvector of A with eigenvalue lambda 2. And third column of P will be an eigenvector of A with eigenvalue lambda 3, and so on and so forth. But the columns of P are linearly independent because P is invertible. And so I have n linearly independent eigenvectors of A. And the eigenvalues are exactly lambda 1, lambda 2, lambda n, and the job is done. So 1 implies 2. 1 implies 2 is done. Now let us prove that 2 implies 1. Let us prove 2 implies 1. Assume that A admits a basis v1, v2, vn of Rn consisting of eigenvectors. Assume we have a basis of Rn consisting of eigenvectors. These basis elements are v1, v2, vn. That means that avj equal to lambda j vj. avj equal to lambda j vj. You take these basis vectors, take these column vectors v1, v2, vn, string them together to create an n cross n matrix P. This n cross n matrix P will be invertible because I had taken n linearly independent vectors in Rn and I created a n cross n matrix using them as columns. So this P will be non-singular. Now let us calculate APEJ. APEJ will be A applied to the jth column of P. The jth column of P is exactly Vj, correct? The jth column of P is exactly Vj, and that is going to be exactly lambda j Vj. That is exactly going to be lambda j times Pej. So we got this equation. So we have checked this equation. Apej cap equal to lambda j Pej cap. This equation has been verified. Why is this true? RHS is Pej cap. There is lambda j Vj. LHS is A times the jth column of P. What is that? Vj. So this equation Avj equal to lambda j Vj translates to Apej cap equal to lambda j Pej cap. Bring the P on the left hand side. P inverse Apej cap equal to lambda j Ej cap. But what is lambda j Ej cap? Lambda j Ej cap is the jth column of the diagonal matrix. The matrix whose diagonal entries are lambda 1, lambda 2, lambda n, 0 everywhere else, is just for abbreviated as diag lambda 1, lambda 2, lambda n. It's pretty clumsy to displaying the whole thing. So diag lambda 1, lambda 2, lambda n is the matrix whose diagonal entries are lambda 1, lambda 2, lambda n, and off diagonal entries are 0. So what is the jth column of that? Lambda j Ej. But jth column of a matrix is that matrix times Ej cap. So we have verified that P inverse AP Ej cap is diag Ej cap. That means that P inverse AP and diag lambda 1, lambda 2, lambda n have the same columns. The jth columns are the same for j equal to 1, 2, 3 up to n. So these two matrices are equal and the job is done. The proof has been completely completed. The proof of the theorem has been completed. A matrix is said to be diagonalizable if it satisfies one and hence both the conditions that it has n linearly independent eigenvectors and there's a non-singular matrix P such that P inverse AP is a diagonal matrix. And the diagonal entries will become then the eigenvalues of A. Suppose, for example, a matrix has n distinct eigenvalues. Suppose a matrix has n distinct eigenvalues, lambda 1, lambda 2, lambda n. Then what happens? Remember, in capsule 11a, we proved a theorem. If lambda 1, lambda 2, lambda k are k distinct eigenvalues, and the eigenvectors are v1, v2, vk, then v1, v2, vk are linearly independent. Here I have n distinct eigenvalues. Take their eigenvectors v1, v2, vn. They will automatically be linearly independent. I have n linearly independent vectors in Rn. They will form a basis. So that means that if a matrix A has n distinct eigenvalues, then A must be diagonalizable. That's a corollary. These two matrices are not diagonalizable. I have already done 0, 1, 0, 0. You can try 1, 1, 0, 1. It's not diagonalizable. These two matrices. It's a general fact that if you perturb a matrix, what do you mean by perturbing a matrix? Take a 2 by 2 matrix, for example. A, B, C, D, a 2 by 2 matrix. Entries are A, B, C, D. Instead of writing the entry, so this 2 by 2 matrix can be thought of as an element of R4. Just instead of writing the entries as A, B, C, D, write it as A, write one below the other, and you can think of a matrix A, B, C, D as a point in R4, for example. So if I give you two matrices, A1, B1, C1, D1, A2, B2, C2, D2, I can think of them as 2 points in R4. And I will say that these two matrices, what is the distance between these two matrices, A1, B1, C1, D1, A2, B2, C2, D2? You simply take the distance between the corresponding points in R4. Square root of A1 minus A2 whole squared plus B1 minus B2 the whole squared plus C1 minus C2 the whole squared plus D1 minus D2 the whole squared. Well, then this will, so you say that two matrices A and B are close to each other. If entry wise, they are close to each other. If the distance between them is small. So idea is that you take a general matrix A, B, C, D. Say for example, you can take this 1, 1, 0, 1. And I perturb this entries ever so slightly. And I don't, for example, I perturb it. I keep the three of the entries same. Fourth entry, I disturb it slightly. 1, 1, 0, 1 plus epsilon. I made it 1. This was non-diagonalizable, but I perturb it, I disturb it ever so slightly. 1, 1, 0, 1 plus epsilon. So I got two matrices 1, 1, 0, 1, 1, 1, 0, 1 plus epsilon. The distance between them is pretty small, right? Because epsilon is going to be a small number. But what about the matrix 1, 1, 0, 1 plus epsilon? For the perturbed matrix, the eigenvalues are going to be 1 and 1 plus epsilon. They're distinct because epsilon is non-zero and it's diagonalizable. So by perturbing a matrix ever so slightly, I can make the eigenvalues distinct. And so if I perturb a matrix, it will become diagonalizable. I can make it diagonalizable. Or the diagonalizable matrices are generic in some sense. Well, I just gave you an illustration, but in general, how do you prove this? The proof will be done in advanced courses if you take one. Now let us bring in two more notions: geometric and algebraic multiplicities. Let A be a n cross n matrix. Then what is the characteristic equation? Determinant of xi minus a. And that's a polynomial of degree n. A polynomial of degree n, I'm going to factorize it completely. Let the roots be complex. Doesn't matter. Let the roots be complex. Lambda 1, lambda 2, lambda t. But lambda 1 may be a repeated root. In which case I'll write it as x minus lambda 1 to the power k1. X minus lambda 2 to the power k2. Dot 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 x minus lambda t to the power kt. These k1, k2, kt are called the algebraic multiplicities of the eigenvalue. The algebraic multiplicity of the eigenvalue lambda j is the multiplicity of lambda j when seen as a root of the characteristic polynomial. Suppose, for example, you have a 5 by 5 matrix A and you compute the characteristic equation and you find that the characteristic polynomial is lambda plus 1 cube into lambda minus 2 squared. You just realize that is the characteristic polynomial. Okay, then you will say that the eigenvalue minus 1 has algebraic multiplicity 3. The eigenvalue 2 has algebraic multiplicity 2. So algebraic multiplicity. Now then we have to go to the geometric multiplicity. Lambda 1 is an eigenvalue of A. Lambda is an eigenvalue of A. Determinant of that means what? That means determinant of A minus lambda I is 0. Determinant of A minus lambda I is 0 means rank of A minus lambda I strictly less than n. The nullity of A minus lambda I is at least 1. The nullity could be 1, the nullity could be 2, the nullity could be 3, the nullity could be n. This nullity of A minus lambda I is called the geometric multiplicity of the eigenvalue lambda. Okay, so algebraic multiplicity and geometric multiplicity. So algebraic multiplicity is what? The multiplicity of the eigenvalue when seen as a root of the characteristic equation. And geometric multiplicity is simply nullity of A minus lambda I. Let us begin with a simple observation. Suppose A is a n cross n matrix and B is A minus lambda I. I created a new matrix B. Then lambda is an eigenvalue of A if and only if 0 is an eigenvalue of B. Completely obvious. I have two matrices A and B. B is simply A minus lambda I. Then lambda is an eigenvalue of A precisely means determinant of A minus lambda I is 0. That means determinant of B is 0. That means 0 is an eigenvalue of B. So lambda is an eigenvalue of A if and only if 0 is an eigenvalue of B. Also, I want you to check that the algebraic multiplicity of lambda as an eigenvalue of A is the same as the algebraic multiplicity of 0 as an eigenvalue of B. I also want you to check that the geometric multiplicity of lambda as an eigenvalue of A is the same as the geometric multiplicity of 0 as an eigenvalue of B. These are very, very simple observations. If you really think about it, you will know why this is so. For the geometric multiplicity, is pretty self-evident because you're looking at B is A minus lambda I. So nullity of B will be nullity of A minus lambda I. But nullity of B is what? Nullity of B minus 0I. So LHS is geometric multiplicity of 0 as an eigenvalue of B. RHS, geometric multiplicity of lambda as an eigenvalue of A. Job is done. So this geometric multiplicity are done. Algebraic multiplicity equality, let me give you a hint. Suppose I give you a quadratic equation. X squared minus 2x plus 1. It has equal roots. Now instead of x, I put x equal to y plus 3. I put x equal to y plus 3. I create a new quadratic equation. Y plus 3 the whole squared minus 2 times y plus 3 plus 1 equal to 0. Do you think this new quadratic equation will also have equal roots? If you can answer this question, and if you try to realize what algebraic multiplicity means and what is it that we are doing here, you will get the answer pretty quickly. You will be able to convince yourself of the correctness of the statement. So you are taking a polynomial equation. F of x is a polynomial. F of x equal to 0. It's a polynomial equation. And suppose you see that 1 is a root. So f of 1 is a root. Now you are looking at a new polynomial g of x, which is f of x plus 3. You are looking at a new polynomial g of x equal to f of x plus 3. You know that 1 is a root. So what is the root of g? Minus 2. Minus 2 is the root of g. Now the multiplicity of 1 as a root of f will be the same as the multiplicity of minus 2 as a root of g. That's all that there is to it in this statement. So I'll stop this lecture here and I'll continue this in the next capsule.